Hey everyone. So today we're going to be taking a look at second derivatives. And this section's kind of, if you can take a derivative once, taking a second derivative isn't too bad. So hopefully this will be an easier section. So a second derivative is just what it sounds like. It is the derivative of a derivative. So if you have some function f, and you take its first derivative f prime, and then you take the derivative of f prime, you're going to get the second derivative, also known as f double prime. You can also call this like d squared y over dx squared, or y double prime. But most commonly we refer to this as something double prime, so f double prime or y double prime. So the second derivative is used frequently when we're talking about concavity. So we say that a function is concave up on an interval from a to b if f prime is increasing on the interval from a to b, and it is concave down if it on the interval from a to b f prime is decreasing. So if you think about what f prime represents on a graph, f prime is the slope. So they're saying if the slope is increasing on an interval, we say it's concave up. If the slope is decreasing on an interval, it's concave down. So if you take a look down here, this is an f double prime. So if the second derivative is positive, it means that f single prime, so the normal derivative, is increasing, and this would be concave up. So we get three images of concave up functions. If you have a smiley face like this, that's concave up, or even kind of like part of a smiley face. These are all concave up. And the way that I like to think about it is, if we take a look here, the slope is negative. Now it's negative, 0, positive, positive, positive. So even though the slope was negative to begin with, it's becoming less negative. The slope is increasing. And that's happening here with this partial smile. It's negative, but it's becoming less negative as we go. And then the last one, well, we're at 0 and now we're positive, so it's clearly increasing. So concave up, just to try to find it in like a picture, it's where you see like a smiley face. Those are concave up functions. Concave down is going to be the opposite. It's where f double prime is negative. That means the slope is decreasing. And it's going to make like a frowny face. So if you looked at the slope, here the slope is positive. Now the slope is 0, now the slope is negative. So going from positive to 0 to negative is an example of the slope decreasing on this interval. And then of course, if you have any part of the frowny face, this is also going to be concave down. Because here positive, less positive, 0, 0, negative, negative, negative. So the rookie mistake with concavity is to confuse concavity with the actual slope. So even if a slope is negative, it could be increasing, as in it is becoming less negative. So here in the first row, example A, though the slope is negative and the graph is falling, this is still concave up because the slope is increasing. Yes, it's negative, but it's becoming less negative. B is also going to be concave up, even though it does have a negative slope to start with, hits 0 and then is positive. And then example C, this is increasing everywhere, and it's going to be concave up. D, even though this is a positive slope all along this interval, it's concave down because it's becoming less positive. E, same thing. It starts out positive, it ends negative. So it's transitioning from positive to negative, so this slope is decreasing again. And then the last one is probably the easiest to see. You start out kind of close to 0 and you just become negative, so the slope is decreasing. So concavity is talking about the change in the slope. So not necessarily the change in the function. Even if a to b is decreasing, we need to take a look at what's happening with the slope on the interval from a to b. So for example 1, it says determine the intervals on which the graph is concave up and on the intervals when it's concave down. And then it says sketch a graph for each function. So they give us f of x equals e to the x. So if I want to measure concavity, we're taking the second derivative. So my first derivative, well, because this is e to the x, the derivative of e to the x is e to the x. And then the second derivative is going to be the derivative of e to the x, which is also e to the x. So if we wanted to make a sign chart of the second derivative, so this is for f double prime, we would want to try to find a critical value. So something we have to ask is e to the x ever 0? And the answer is no. There are no critical values here. E to the x is never 0. So we're either going to be concave up the whole time or concave down the whole time. So let's plug in any test value. Let's plug in 1. E to the 1 is e. E is 2.7 and so on. So that's a positive number, meaning we are concave up on this whole interval. So what does the function look like? Well, this is going to go back to, do you remember what exponentials look like? When x is negative, it is very close to 0, and then we hit our mark and we go up. This is what an exponential function looks like, and as you can tell, that is part of a smiley face. That is why we are concave up the entire time. So for example 2, same thing as example 1, but this time we're working with ln(x). Now, you might remember what the natural log looks like. Let's see here. We can't be 0. We look something like this, which you might right away be able to tell that's concave down. But let's verify it by taking the second derivative. So my first derivative, g prime, the derivative of of ln x is 1 over x. And I can rewrite this as x to the negative 1. So to take my second derivative, this is just going to be a power rule. This is going to be negative x to the negative 2, which as a fraction is negative 1 over x squared. So now we can ask, well, is this ever 0? And no, it's never going to be 0. If we plug in bigger and bigger and bigger values for x, this will get closer and closer and closer to 0, but the function itself is never 0, meaning we are going to be constantly concave up or concave down. So let's plug in a test value. And we do have a restriction. We do have ln is not defined for 0 or negatives, so we need to be on the interval from 0 to infinity. Just as a starting point, we have to be at 0 to infinity. And this should be an open bracket because we can't be 0. So we're not going to worry about negative values. So let's plug in something bigger than 0. How about 1? If I plug in 1, I'm going to get g double prime of 1 is negative 1 over 1 squared, which is 1, negative 1. So this is a concave down function the entire time, which is also what we predicted when we graphed it to begin with. So normally when we're dealing with these kind of problems, we won't know what the graph looks like. It'll be something more complicated. Because we know what the natural log looks like, we could tell from the very beginning this is a concave down function or part of a frowny face, but we verified it by taking the second derivative. All right, example 3, same instructions as the first two, and we're dealing with the function h of x equals x cubed. So this one's actually going to be, is going to have a point where the inflection does change. So if you remember, a cubic function will look something like this. So as you can tell, we will have a concave down portion, and then we're going to have a concave up portion. But now let's just imagine that we didn't know what this looked like. So let's do the math. H prime of x is going to be 3x squared. So h double prime of x is 6x. Now, is 6x ever 0? Yeah, it's when x equals 0. this is a critical point. So we make our number line, we put in a 0. So now I need something smaller than 0, I need something bigger than 0. And remember, we are dealing with h double prime here. So h double prime is just 6x. So if I plug in something negative, I'm going to get a negative number. And if I plug in something positive, I will get a positive number. So I'm concave down when it's negative, concave up when it's positive. So here's my concave down. And here is my concave up. We can put this in an official notation, concave down on the interval negative infinity to 0, concave up from 0 to infinity. Finding inflection points. So an inflection point is a point on the graph where the function changes its concavity. So either it goes from concave up to concave down, or concave down to concave up. And for the concavity to change at a point, f double prime must change signs at that point. So this takes us to theorem 1, where it says that if y equals f of x, and it's a continuous function on the interval from a to b, and it has an inflection point at x equals c, then either f double prime of c equals 0, or f double prime of c does not exist. And this is kind of what we were talking about back with maxes and mins for the first derivative. We would find when is the derivative 0 or does not exist, and those would be critical values for maxes and mins. For inflection points, we look at the second derivative, check when that's equal to 0 or does not exist, and that gives us our inflection points, where it is concave up or concave down on different intervals. So at the bottom, we've got 4 pictures here. So we have concave up to concave down, and you see we get part of a smiley face, followed by part of a frowny face. So that's concave up to concave down. We get concave down to concave up. It's frowny and then smiley. Concave up to concave down, we got smiley face, frowny face. And here we have concave down does not exist to concave up. So it's frowny face, almost a vertical line here, concave up. Here on example 4, they're saying find the inflection points of f of x equals x cubed minus 6x squared plus 9 plus 1. So remember, for an inflection point to occur, the concavity has to change either up to down or down to up. And we get concavity by taking a look at the second derivative. So the first thing we're going to do is take the derivative twice. So f prime of x, well, that's going to be 3x squared minus 12x plus 9. And now f double prime is going to be 6x minus 12. So let's find some critical values. So 6x minus 12 equals 0. 6x equals 12, so x equals 2. So we have a critical value at 2. So if we have an inflection point, it's going to happen at x equals 2. And this is a number line for f double prime of x. So I just need to plug in a value less than 2 and see what happens, and a value greater than 2. And we're looking at f double prime. So that's the 6x minus 12. So let's plug in 0. 0 minus 12 is negative 12, so this will be concave down. And if I plug in something bigger than 2, let's say 3, 6 times 3 is 18, minus 12 is 6, so it's going to be positive. So I have concave down, I have concave up, meaning 2, or x equals 2 is an inflection point. So I have an inflection point at x equals 2. Now, depending on who your teacher is, they might actually want the point. We're just getting one coordinate, we get x. But where is this? What is the y value? If I want the y value, I need to look at f of 2. So it's going to be 2 cubed, 8, minus 6 times 2 squared, so that's minus 24, plus 9 times 2, that's 18, plus 1. So let's take a look at that. 8 plus 18 is 26, plus 1 is 27, minus 24 is 3. So it would be at the point 2, 3. So when they ask for an inflection point, you should give a coordinate pair, but some teachers are more relaxed than others when it comes to that. Example 5, this is our last problem for the day, and they're giving us a beast here. So we want to find the inflection points of f of x equals the ln of x squared minus 4x plus 5. So the first thing we got to do is we need to take the derivative. So f prime of x, well, this is going to require a chain rule. So we're going to do 1 over x squared minus 4x plus 5 times the derivative of the inside, so that's 2x minus 4. So that gives us 2x minus 4 over x squared minus 4x plus 5. So that's first derivative, but for inflection points we need the second derivative. So f double prime, and now this is going to be a quotient rule. So remember, quotient rule is bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. So from here, derivative of the bottom. We can go ahead and write this out. We know that the top is 2x minus 4, so the derivative of the top is 2. The bottom is x squared minus 4x plus 5, and the derivative is 2x minus 4. So when we go ahead and plug this in, we're going to get something pretty long here. It's going to be x squared minus 4x plus 5 times 2 minus 2x minus 4 times 2x minus 4. And in the bottom, we have x squared minus 4x plus 5 squared. So the hope is that this will clean up in some way, and fortunately it does. So multiplying the tops together, we will get 2x squared minus 8x plus 10 minus, and now I've got to multiply 2x minus 4 times 2x minus 4. It'll be 4x squared minus 16x plus 16. Now don't forget to distribute your negative sign. Also the bottom, we still have x squared minus 4x plus 5 squared. So don't forget to distribute your negative sign. But when we do that, we're going to get 2x squared minus 4x squared, so that's negative 2x squared. Negative 8x minus negative 16x, so that's going to be plus 8x. And then 10 minus 16, that will give us a negative 6. All over x squared minus 4x plus 5 squared. So I'm going to continue on the next slide just because we're running out of room, but we're almost done with the problem. So when we left off, we were at negative 2x squared plus 8x minus 6 all over x squared minus 4x plus 5 squared. In the top, I can factor out a 2, or a negative 2, so it'll be negative 2, times x squared minus 4x plus 3. And in the bottom, I still have x squared minus 4x plus 5 squared. And now x squared minus 4x plus 3 does factor. So this is going to be negative 2. And the factors are negative 3 and negative 1. So x minus 3, x minus 1 over x squared minus 4x plus 5 squared. Now something to note here, the denominator, the x squared minus 4x plus 5, this is going to be strictly positive. There's no value of x that we can plug in to get a negative here. So the only way that we can get a 0 is in the numerator. and that would be at x equals 3 and at x equals 1. So those are our two critical values. We've got 1 and 3. So we need to do a sign chart. So f double prime of x. So if I plug in something less than 1, so let's plug in 0. If I plug in 0, my numerator is going to be -2 times -3 times -1 divided by 5 squared. So it's definitely going to be something negative in the numerator divided by something positive in the denominator, which is negative. Oh, wait. So negative, that was because we plugged in 0, so that's in the middle. Let's see what happens if it's something less than 1, or sorry. I'm getting ahead of myself. Between 1 and 3, so we already did 0. Between 1 and 3, let's plug in 2. If I plug in 2, I'm going to get -2 times -1, so that's positive, times 1, which is positive. In the denominator, I'm getting something positive, so this will be positives in the middle, not negatives. And then let's see what happens if I plug in something bigger than 3. I'll get -2 times something positive divided by something positive, and that's negative. So the inflection points have to be at x equals 1 and x equals 3. And if we wanted to find the y values, we would have to plug in up here for f. So we need f of 1 and we would need f of 3. But unfortunately, I don't think we're going to get anything super nice here. If I plug in 1, I'm going to get 1 squared minus 4 plus 5. That's the ln of 2, which is irrational. And if I plug in 3, I'm also going to get the ln of 2. So I mean, my points would be 1 ln of 2 and 3 ln of 2. These would be my two inflection points. Not super pretty, but these types of problems are out there where we don't have an image of this. In fact, maybe I'll look up this image, put it on the next slide just so we can really take a look at our answer to make sure we're right. But this is how we calculate for inflection points. First derivative, then the second derivative, find when the second derivative is 0 or does not exist, and then do a sign chart. So yeah, let me see if I can't find this image. I'll put it on the next slide. And that is example 5. So using Wolfram Alpha, I was able to get a graph of our function, the ln of x squared minus 4x plus 5. And I asked it to plot our inflection points, which you can see here at 1 and 3. And then for the y value, we were calculating the ln of 2. And the ln of 2 is definitely between 0 and 1. And that's what we're getting here. So I don't know the exact numerical value, but I would believe that this is the ln of 2. So yeah, we nailed it. Our inflection points are at 1 ln of 2 and 3 ln of 2. So just some closing thoughts on this section. I hope that made sense to everyone. Concavity and second derivatives, they're not too bad. I find, especially if you're working with polynomials, taking a second derivative is easy because whatever the first derivative is, like the powers are going down. It can get more complicated when we have ln's, kind of like in example 5. We're taking the second derivative, then required a quotient rule. But the idea is that if you can take the derivative once, hopefully we are able to do it a second time without too much effort. And that's what this section is all about. So if you got any questions, feel free to reach out. The homework should already be posted, and I'll see you in the next video.